SwayamPrabha. Digital India. Educated India.
Jnanam Paramam Dhyayam. Knowledge is supreme.
Welcome to MOOC course on applications of interactomics using genomics and proteomics technologies. Today's lecture will also be delivered by Mr. Sushil Vaidya in continuation of his previous lecture and discussion about BLI technology. This time he is going to conduct the hands-on session and show you how to perform this experiment on biological samples of interest. I am sure now you will be able to understand the principles much better and also get a fair understanding about the protocols and the technology, how to use that for your own experiments. So, let me welcome Mr. Vaidya again for this demonstration session, which I am sure going to be very stimulating for you.
We had seen the BLI presentation, what the technology behind in the BLI as well as the few applications. Now we can do the experiment, how easily we can do the kinetic studies using the BLI technology. Sorry for actually, like I was planning to project the screen on the projector, so but I unable to do that. So using this we can with a connected to the server workstation we can do the experiments. So what exactly we are doing here is the first experiment I am going to start is the kinetics here. The kinetics experiment, what I am going to do is the first experiment. So kinetics and affinity measurements using the first experiment we are doing the affinity measurements as well as the kinetic rates constants for the mouse monoclonal antibodies using the protein A as a ligand. What I am going to do here is the first I will put the first column in the 96 well plate here, the buffer. The buffer is the SD buffer, the sample diluent, and the second column I will put the biotinylated the protein A as a ligand, and the third column once again I put a buffer. The buffer is here is the SD buffer, the sample diluent buffer, which consists of your PBS, PS 7.4 as well as the tween 20.02% and the 0.1% BSA. So why, you can ask, so many components are in the buffer. So generally why we are adding the surfactants as well as the BSA is like it reduces the non-specific interactions. Generally protein have a charged species have a tendency to bind to any solid support. To reduce this non-specific binding, what we are doing is we are adding a surfactants and as well as the blocking agents like the BSA. In case of the ELISA, you are adding a BSA or the surfactants like tween 20 or the Triton X100s or any other surfactants like NP40 and all that. Now we are using same thing in the buffer systems, the PBS buffer, it is a PS 7.4 as well as consists of the BSA and tween 20. And then the last column, if you look at the sample column number 4 is your mouse monoclonal antibody. We have a serial threefold dilutions, we will do it, and then we can study the interaction between the mouse monoclonal antibody to the protein A ligand. So this is what the experimental plan. What the concentrations we can look at before that. The biotinylated protein A ligand, I will take it around 1.2 microgram per ml. That much concentration is good enough for the immobilization of the biotinylated ligand protein A. And the mouse monoclonal antibody, I will take it around 10 microgram per ml is the concentration is equal to around 66.6 nanomolar. Using 66, that is the highest concentration, we will go threefold dilutions using that. Around 6 titration series we can do using that. So one last column I will put it as a blank buffer, just only a SD buffer. So why we need a referencing is like that, sometimes even the buffer can give artifacts, system can generate artifacts. To subtract those data, we need a blank reference. So we can with using a 7 we have a 8 channel, we can either go with the entire 8 channel or just only 7 channel, or you want to just test it on a single sample, that is also possible. It is need not like that you have to, if it is 8 channel, you have to go with 8 channel. If you have one sample with a one sensor, you can do it, or 3 samples, you have a 3 sensor, you can do it. It depends upon how you are going to design your template. And these are the concentration, very simple, and I'm taking about the time around 30 seconds is my baseline time, just, and the 120 seconds I will look for the loading, how much load it happens on that, and the software have a compatibility, like you can extend when you are doing the acquisition itself, you want extend some more time, it is possible, or you see that there is a saturation happens, then you want to just jump to the next step, yes, that is also possible. This feature is not in case of the SPR. Once you fix this time, you can't change. But in case of the BLI technology, it's a possibility like that you can play around with the timings. And the next baseline I will do for a 60 seconds, where once the immobilization is happened, then the unbound molecule you want to wash up. We need a stable baseline, then we can using 60 seconds is good enough. I will do the 120 seconds association, where your antibody binds to the immobilized protein A, and then dissociation I will do it around 120 seconds. The 3 around 5 minutes around, roughly if you take it around, hardly it's not more than 15 minutes. So in a 15 minutes you will finish off your entire kinetics experiment in a one goal. In comparison with the SPR, so one injection, say suppose after immobilization, it is a 3 to 4 minutes immobilization, then each concentration, say suppose you are injecting a 1 nanomolar solution, 1 nanomolar concentration, 120 seconds is 2 minutes and then the 3 seconds. So totally 5 minutes is the one concentration you are. So if you are doing for a 6 concentration, it is roughly a half an hour time, more than half an hour it is. After the regeneration, then washing, then the injecting the same samples over the immobilized surface, it is roughly more than a 1 hour experiment. But you can quickly finish off in a 15 to 20 minutes of time. So where you can get the fast, the determining your the kinetic rates constants, and then easily quickly screen the experiment, which is the binders, which are not binders in case of the screening experiments. If you are doing the full maturity kind of experiments where you want to get the full kinetics pattern, then you can easily quickly develop a method and then get the KD value. In comparison, I can say that why the SPR and the BLIs are faster. So suppose when you are developing a method, you don't know how much I have to immobilize on my sensor surface. That you can quickly screen on the sensor on the different concentration. If I put the immobilizing molecule on the sensor surface, say suppose 1 microgram per ml, 5 microgram per ml, 10 microgram per ml, then we go for the further association. So suppose 1 microgram per ml, I am getting a response of around 0.5 nanometer, and 5 microgram per ml concentration also I am getting a around 0.5 nanometer response. Then you can compare, say whether I need to immobilize higher concentration or lower concentration, because 1 microgram per ml also getting a 0.5 response, and 5 microgram per ml concentration also are getting the 0.5 response. Then the question is like whether you required to overload on the sensor surface using the concentration. So what happens is in the label-free platforms, if you have more concentration, you start immobilizing on the sensor surface, there is a possibility that steric hindrance happens. There is a one molecule binds here, there is a one more molecules immobilized here, and one more molecule. So your binding pockets are something like very close to each other. There may be possibilities that due to the more crowding on the sensor surface, there is a possibility of less binding, or sometimes it leads to a non-specific binding, or you can see the biphasic associations. These are the different ways when you are looking at the interpretation of the sensograms, what we call it as, we are getting the data, the binding curves, we call it as sensograms. Looking at the sensograms, whether it is a 1:1 binding model or a 2:1 binding model or a 1:2 binding model, so easily we can look at it using those sensograms. So now we can start the experiment. It's just only the sample preparation time takes us some in that, but the operation time on the instrument is something like very quickly you can get the data. So is anybody would like to do with me for the sample preparation? Fine? Yes, please. So this is the 96 well plate, black plates we are using. It is not a transparent plate, just it is a plastic plates, polypropylene flat bottom plates we are using in the entire experiment. Why, you can ask, why we have to use a black plate rather than the transparent plate? The question is here is, it is works on the interference based technology. Light will be passed through the sensor. So I can show you, these are the sensors. Typically it's like this. If you can come around here, you can see that how exactly it looks like. Or later also, once the experiment is done, you can look it into that. These are the typically the sensors. Yeah, either you can pass this tray to everyone there, how it looks. So typically it looks like your injection needle. Everything is happening at the tip of the surface, the interactions. Just the surface area of this, the fiber optic is just only 600 micrometer in diameter. Okay. Well capacity is 390 ml. Sorry, 390 microliter. But the minimum dipping volume what we are working is 2. So here we have a SD buffer. Okay, the sample diluent buffer. So it consists of a previous BS 7.4 and queen as well as the BS in that. So a liquid 200 microliter in all the wells. The first well. You look at on side by side, what we are doing is here. These sensors are actually a dry coated. The streptavidin, what I am using the sensor here is the streptavidin chemistry. So I have a bioaccumulated protein A with you. So what I am doing is these sensors I will hydrate with this buffer. So the minimum hydration time is 10 minutes. So a liquid 200 microliter in this well. Each. Yeah. The first column 1 and column 3 you can put 200 microliter of the 200 microliter each well. Column 1 to 7. So on side by side, what I am doing is I had taken one more plate here. I had already added the 200 microliter each of the same buffer. I am placing this like this in the groove. So this is the sensor tray. This is a 96 well plate format once again. So these are the 7 streptavidin sensors I had taken here, and then I'm carefully putting like this. So it will be like I did it up to G. Okay. Then you can add column 3. Only the time is making a plate, that's all. The rest, once you make a program, it is unattended, just to leave it there.
You didn't add in H?
No, not required, just 8 G, that's good enough, not H. We are doing with the 7 sensors. Okay, then now I have a protein A here, the biotinolated protein A, it is a 250 microgram per ml. Okay, take around 15 microliter from this. Then make up to 1500 microliter.
We should let others do it.
Yeah. Take around the 15 microliter diluted to 1.5 ml. Take one mg, and I have the most normal antibody. It is 1 mg per ml I am having. Okay, I have 20 microliter here. Okay, then take a 10 microliter. This corresponds to a 10 microgram. The 10 microgram is placed into the 1 ml of this. It's nothing but
1.5 ml of this and 15 ml of sample.
Means 1485 microliter.
And 15 of that?
15 of that, let's see, corresponds to it. It's a 1.2 microgram per ml of the biotin liquid protein. Thoroughly pipetted, mix it properly. So why I wanted to make you guys, let's say you feel that how exactly. Very simple to operate. So then you allocate the 200 microliter of this in each bit. Yeah.
In the second one.
So don't you use it like a slant, so there should not be air bubble, right?
There's 7 years.
Fine, done. So now we have to make the binding partner, the most monoclonal antibody. So this is exactly 1 mg per ml. I have 20 microliter here. Take a 10 microliter or a 5 microliter, transfer to the corresponding 1 ml or 500 microliter. So okay, then I feel take a 5 microliter, put it into 500 microliter. So it corresponds to 10 microgram and the concentration, the strength. So transfer 300 here and rest well you put it buffer and then serial do the serial. 100 microliter take it, transfer and then thoroughly mix it. Then take 100, then mix it. Okay, or otherwise I will do it, not a problem here. Okay. So last one is buffer.
it here. 200. You can ask. I will once again. I will transfer here only. In this well, first well itself. I can then. I will. I will take this 100, then transfer. So last well I kept it blank because zero concentrations. Okay, okay, we have done the plate preparation. Now we can go for the experimental plan. So now the experimental plan, we have two softwares here. The software, one for the acquisition and the other for the data analysis. So in the first acquisition, we are acquiring the data. Once the acquired data, we have to go for the data analysis. So the two softwares. So first what we'll do is we'll go for the acquisition. I'm going to do double click on this. So when you do double click, the instrument starts initialization. It's go back and forth. So you can see the sound. It will take roughly around 30 seconds for the initialization. In comparison to SPR, when you start the experiment, you have to pass the buffers, stabilize the flow and all that. Here nothing is there. Just come morning, switch on the instrument, allow for 40 minutes, then stabilize. Just the lamp has to be warm up here. Nothing is there. If you now look at, there is a status which is showing that initialization. So it will go XYZ direction alignment. Then it will come message as a ready here. It says roughly a 30 seconds initialization. So now you can see that the instrument is ready. So we can start the experiment. So when you click on the software acquisition, data acquisition, then you can see there is a wizard. In the wizard, what kind of experiments you wanted to do, whether you wanted to do a kinetic study or you wanted to do a quantitation study. So we have an option here, kinetics as well as quantitation. So our interest is here, kinetics experiments. So we can do the epitope binning also. There is one more software here for that. So I will now check the kinetics experiments. Here I am clicking on. Then the screen mark I have to say go. Using this, I will take a blank experiment here. There are some inbuilt templates are there, but this is the best way to go for a blank experiments where you can make your own template format. So if you know the blank templates, how to make it your experimental design, it's very quick. So I will say go on the click here. Now if you look at this, the window, if you look at this is your plate format here, you can see there are different panes here. One is called as a plate definition, assay definition, sensor assignment, review experiment and run experiments. So these are different, these are the 5 actually pages are there, you can design those. So what exactly the plate definition? You had to feed the information, what are all things you added in the plate. So what we had in the column number 1, this is 96 12-bit format, column number 1, first we had placed a buffer. The second column we had load. The third column is once again the buffer, the fourth column is sample, the underlying. So just we had to assign those informations. So how we are doing this? Buffer. The fourth is your sample. So assign as sample. But I am using only 7 sensors, not all the 8 sensors. What I will do is I will just select it, remove it. So just only 7th and the sample with 6 concentrations and 1 next to the blank. Or if you want to assign this last column as a blank, a buffer, that also you can assign like this.
So these are the plate definition. We had to feed here in the template. So in the sample ID, what you had feed the buffer. Okay. So Control C, typically your looks like Excel sheet. Okay. Then the load, you have a bio protein A. Then once again you had buffer, right? Control C, and then you can go with the buffer. Then you have a mouse IgG. Okay. So here the important is mouse IgG, you have to mention your concentration, because if you not feed the concentration, you will not get the KD value. So concentration is the one of the parameter when you are calculating the KD, kinetic constant, rate constants. So one of the concentration parameter is important. So what is the general IgG KD is 150 kilodalton. So we have to feed the 150 kilodalton here, the molecular weight KD cutoff, then Control C, once again you required all the parameter. So my starting concentration is, the top concentration is 10 microgram per ml. So just if I type it 10 microgram per ml, here the concentration 10 microgram per ml, software have a, you can change the concentration parameter like concentration microgram per ml or mg per ml or anything. And the next, even automatically when you put the 10 microgram per ml, then when you put the KD value, the size of the protein, then automatically it calculates the 66.67 nanomolar of your 10 microgram of IgG corresponds to the 66 nanomolar roughly. So what I will do is just I will select all this. Okay, I will right click it, I will set well data. Then I have an option here whether I can go with the concentration basis or the molar concentration basis. My concentration basis is around 10 microgram per ml is the stock, divided by, I had done a 3-fold dilution. So what I will do is just I will type it 10 divided by 3. Then I will choose, I had done a programming in such a way that top to bottom, right? Then what I will do, divide 10, I will choose a template here is the down. The black dot is the one which is the highest top concentration, the lighter one is the lowest. I am using this format. If you have feeded this information, you can put it in that way, or you can low to top, then that also possible. Then I will say that OK. Then automatically when you choose this, then you have a 3-fold dilution. So the KD range covering from 66.67 nanomolar, it all the way 6 concentration 3-fold, it is 0.2 nanomolar. Around it's roughly equivalent to 200 picomolar. So these are the things you had fed in the plate definition. Then the next is the assay definition. The plate we had fed, but we have to tell the software, you have to go, this is the first step, this is the second step. You have to assign that. Then only instrument move according to the respective wells. So what is your, what are all the information we have to feed in this? Here there is a section called as add. In the add, when you go click on this, what we are doing a baseline, we are doing a loading, we are doing a association, as well as we are going to do dissociation. So those informations we have to add. So what here is association, I have to click it, dissociation I have to click it, baseline, by default there is a one baseline is there already. You need a one more baseline. Yes, we have 2 buffer columns, that's why I am adding a one more baseline. And what apart from that, we have a loading. Loading is nothing but the immobilization. So I will just click it, then say OK. So it will ask, the step name baseline already exists, because it already is there. Do you need one more? Yes. So these are the steps. We have to assign instrument go according to the backend flow, the robotic arm. So what is the first step here? I will take this arrow mark using this, and I will double click on this. It is just cross mark. So first step is your baseline. Then the next step is what? It is a loading. So I will take this arrow mark, then once again double click on this. It is a load. Then the third, I have one more baseline 2. I will double click on this. Then the fourth is your association. Double click on this. And the dissociation, you can ask where exactly the dissociation happens. I will do it in the column number 3. Once again, same buffer. I will do it. So 1, 2, 3, 4, 3. The step is first column, the robotic arm move to first, it will dip into the first well, goes to the second, then the third, fourth, and back to third. So then you can assign how much time I have to do it. 60 seconds generally I will go, or 30 seconds or 60 seconds I will go for the baseline. So just we will go for a baseline, this one. Association time generally I will go for around 120 seconds is just 2 minutes time. And the dissociation I will go for around 3 minutes, 180 seconds. And the baseline to how much you require, 60 seconds, one more. And the loading time, how much, I will do it around 120 seconds. Let's take it, assume just we will take it 5 minutes. These, I will tell you, these SPR kind of, in this one, it is has to be based on the experience you have to put it. It's not like that. General assumption is like that minimum is 300 seconds, 200 seconds we put it. So just I had put 300 seconds. But in beginning I have mentioned that software have an option, I can jump to next step. If I feel that the concentration is good enough, this is good enough for my binding, I can jump to next step. Or still if you feel that yeah, it is not enough, you can extend the time, that particular time, still the loading. So I will put a general around 300 seconds. If we feel that it is around roughly 0.5 to 1 nanometer, if it is loading is happening, then we can jump to the next step. Okay, then I am using a streptavidin sensor, around roughly experimental time is totally 13 minutes, but even less than that it will be probably. Okay, these are the, according to that sensor will move. And the next is sensor assignment. In the talk you had seen that there is a sensor compartment as well as the sample compartment. Sensor compartment where you are placing your sensor tray, the sample compartment where exactly you are placing your sample plates. So you can see here. So this is also 96 well plate format. So I have to tell the instrument which column the sensor has to be pick up. Okay. By default it is a 1. Suppose you had put your sensor somewhere in the column number 8, what you can do is just say remove it, then automatically it will think that sensor you had placed at column number 8, it will pick up the sensor from that particular position and then read. Okay. So now by default I had placed. Okay. Then when you are doing a QC kind of your experiments and all that, you can provide your lot number for your sensors, because it's a very important when you do it in an industry kind of setups where exactly QC monitors those lot numbers what you had tested and all that. So that is one important, or if you have any other information you want to feed, that also fine. Then the review experiment. Before going to start your experiment, whether whatever I had set up the experiment is fine or not. So this is your sensor compartment, sensor tray where we are placed. This is your sample plate. If you just look at here using this arrow mark, just in these sensors are highlighted by the border black color. If you look at here, the sensor is picking from the column number 1 and it is highlighted by the black color. The first well it is going there, then it is going to the second column, then the third, then the fourth and back here. So my experiment setup is fine. Sometimes what happens, we are running so many sample, there is a possibility that you will miss the steps. So it is best way to review the experiment, whether my sensor is moving in a proper way or not. If it is something you missed while the numbering, you can go back and then reassign it.
So that's the actual real time that it's doing all those steps?
Yes, yes.
It seemed like it was going very fast.
Yeah, it's a program.
It just dips very quickly, that's all it needs to do?
Yeah, based on the timing here, this is the review. Prior to the experiment, we are reviewing whether my experiment setup is fine or not. So these are the timings I had provided here.
Right, I see.
So then when we are reviewing the experiment, before starting the experiment, yeah. And the run experiment, the last here, where you want to save your data, the path we have to provide. So I will click here and the desktop, I will create a new folder, IIT demo. Sorry. Okay, I will choose this folder. Temperature, we are 23 degree, we are working at room temperature now. This instrument you can work from 15 degree to 40 degree. Set, you can set and allows for stabilization of the, it have Peltier. So the next, what is your experiment name? So I will just mention as the kinetics, okay. Then here in the, if you look at come here, run settings, delay experiment start and the shake sample plate while waiting. What exactly this is? I mentioned in the earlier, sensor comes with a dry actually, these are dry sucrose coating, but we have to hydrate in your buffer. What buffer you are using for your experiment, the sensor has to be hydrated. Minimum hydration time is at 10 minutes. Okay, so what I did was, during my sample preparation itself, first I started a hydration, I started the sample preparation. So I saved my time. Otherwise, if you forgot this one, hydration, then you can check in this. So after 10 minutes, experiment will start. Or otherwise, if you want another 20 minutes also, you can assign the time, how much you required. During the hydration time, whether your sample placed has to be in the shaking condition. I mentioned it is not a fluidics based, it works on the dip and rate. So samples will be in the shaking condition. Generally not. What happens is, during the waiting period you are in the shaking, protein have a tendency to aggregate when it's one there's a possibility. Generally we not advise that. Okay. Then I will uncheck this. During only experiments we require a shaking. During hydration not required. So then you can mention the this plate temperature. You want to work from 15 degree to 40 degree. Now it is around room temperature 23 degree. So even after the experiment, do you want to hold that temperature once again back to 23? Yes, you can click it, not a problem. So after this is what we have done the experiment plus the setup, you can say. Then we can say start go. So before going to that, we have to place the sensor as well as my sample tray in the instrument, right? So where my sensor tray is here, okay. These are the 7 sensors I am using. I am placing here in the. Sorry, I can't show you this one. Once after the experiment, you can guys look into that. I will place here, and my sample plate.
So we had placed all the both, then we can say go. So when you say go, we have started experiment. There is a one warning message. It will be the black. So these are the statuses. This has picked up. There are some incubation times and all. So now if you look at it, it's dipping in the first well containing a buffer. Nothing is there. It's kind of a very noisy data. Nothing is there. 60 seconds will acquire the baseline. So as I mentioned, we have software we can extend the time as well as we jump to the another one good advantage.
So nothing is binding. That's why there is no interference changes from the sensor tape.
And why are they spreading like that? Data was really tight at the beginning and now they're all spreading out?
Probably the well volume and all that. So now if you look at here,
Okay,
now the binding is happening. The protein A is coating to the streptavidin layer. So as the molecules binding to the sensor surface, gradually rising the sensogram in that. This, as the molecules bind to sensor surface, you can see the shift in the sensogram. I had done around 300 seconds I had put for this. Around by 50 seconds, I am almost, my criteria is more than 0.5 nanometer, between 0.5 to 1 nanometer, I should get a loading. That's good enough for me for interaction studies. I don't want to even overcrowd on the sensor surface, the immobilization. So even I can go to the next step. I will do it around 1 nanometer loading, then we can study that.
What's the affinity constant range that this works well in?
From 10 picomolar to 1 millimolar you can go. That is the broad, on par with your Biacore. So around, that's good enough for me, I think, loading. One nanometer. Okay, fine. I'm going to the next step. It's good enough for me, the immobilization level. Next, if you look at this columns, green highlighted by the particular step is happening. Now if you look at the next step is the baseline, where if it is there any unbound molecule just get washed off in that. And very negligible, the amount is very negligible, whatever you are immobilizing. You have, in the well you have so much, but when it is bind to sensor surface, it's very little. So 60 seconds will be your baseline. It's a more stable baseline, what I'm observing. 30 seconds is good enough. I can jump to next step. I need a very stable baseline. Sometimes what happens is, due to there is a, maybe you can observe a drift and all that. So this is very stable baseline. The drift probably comes from different components in your buffer systems that play important role. When you have protein, you have stabilized with some surfactants or some other components. You have diluted in a different buffer altogether when you are doing dilution. That probably sometimes causes those drifts. So if you look at now, the next step is the association. It moves to the association. Here if you look at, I'm aligning the data. This is the first concentration 10 microgram per ml, then the next 10, then the 3.3 microgram per ml. This is your most monoco antibody binding to the immobilized protein A. Very simple experiment. So nice dose distribution. So I think lower ones are not picking up. It is in the sense it is too diluted, the samples, or otherwise we have to extend the time. It has to come very nicely dose distribution, because we had just put around 120 seconds. Probably we have to extend to some more, another 60 or 120 seconds. So the lower also will come very nicely. So let's acquire for 120 seconds. So we are actually, I forgot to mention, we are working with 1000 RPM. So we have a shaker range working from 100 RPM to 1500 RPM. Depending upon the applications, we can choose the right RPM. Generally, when we are working with the kinetics experiments, we go with 1000 RPM by default. When we do the quantitation experiments, we generally work with 400 RPM. where we are working with a microgram level concentrations like 200 to 1 microgram in that range, that's fine. When you are working with a concentrations like in kinetics experiments, we go with the. So now it move back to the dissociation step. You can observe the bond molecule start dissociating. So just I am doing around 180 seconds. Generally either any SPR or if you take it a BLI technologies. So dissociation rate, it's a 5% or 5 to 10% dissociation is good enough to calculate the KD value. It is need not like that you have, say suppose I am giving an example, you immobilized a 100 molecule on the sensor surface, then your 100 analyte will bind to the sensor surface, then it is need not like that all 100 molecule has to dissociate. Just 10 molecule if you get dissociation, you typically observes like this. That's good enough for you to calculate the kinetic constants as well as the.
So when you say 10%, you mean 10% of the signal height? If it comes down by 10%, then you're.
Yeah, that's enough. Good enough.
That's how you do it.
Yeah.
So that's enough time.
Even SPR also same. It's good enough. Need not like that we have to dissociate completely all.
Yeah.
That's why we go with there is a condition called as a regeneration. So rest 90 is bound to your sensor surface, right? Using some agents like higher salt strength solutions like 1 molar or 2 molar sodium chloride or a magnesium chloride, or if you want to change the pH like glycine pH 2 or pH 1.5, 10 millimolar glycine, that's good enough. Or we will go with a 50 millimolar sodium hydroxide solution. So that will remove the remaining bound analyte. So one thing we have to consider when you are doing the regeneration is stability of your ligand. Whatever you had immobilized on the sensor surface, that should be stable after the regeneration. There may be sometimes what happens if you are using some conditions like glycine or some higher like a base site, primarily your protein undergoes a denaturation. So then next experiment we can't use the sensor back. So that's why we have to carefully consider the regeneration solutions. When we test the compounds, like small molecules generally comes in that range, nanomolar to micromolar range. So that time we start with some 100 micromolar. Beyond, if you are trying with that concentration is a point of.
So that's an interesting question. With Biocore, the size of the interactor, the analyte they call it.
Mass change actually.
Well, the bigger it is, the easier it is to detect.
Yeah.
Is that an issue here? Does this
It's similar. As the low, the size wise the molecule as a very small, then you can see a noisy sensograms. Even in Biocore also same.
Yeah, I know. Biocore is definitely that way.
So similar. We also yeah. As bigger molecules bind to sensor surface, you get a nice sensogram.
I see. So yeah.
So I think it is done.
How low can you go? What's the smallest that you can?
150 Dalton.
150 Dalton.
Yeah.
Okay, so it's about the same.
Same. So I think now status saying that instrument is ready, experiment is finished, and here also is saying that experiment is complete. So we got a data. Now we have to go for the data analysis. So what we got a data for using from this. So I will minimize this. Then I will go for the data analysis. I am here. I will double click on the data analysis. Okay. Then I am on my left hand side on the bottom where your data is stored. So here I have a folder called IIT demo. I will drop down here. Then I will click on the kinetics. The experiment name I provided is the kinetics. The pink color file here is just I will double click on this. When I double click, automatically the kinetics data will be opened here because I started the experiment in a kinetics mode. So we have a quantitation mode. If you are run an experiment in quantitation mode, the data will open in the quantitation. If it is kinetics, it will open in the kinetics. So I will click on this. Okay, this is what the data is get opened. In the processing section, I need to process the data. So what I have to do, I have to subtract the blank from the reference well from the rest of this one. So why I mentioned, because sometimes buffer also gives the artifacts. So we have to subtract those data. This is the raw data, entire view here, raw data view and alignment and all that. You can particularly click on these and this is what the data is, your association and the dissociation. Okay. So here in the top section here, sensor selection, what I have to do is I have to do the subtraction. I had put a here 0 concentration. What I will do is just I will select this, right click it, change well type to a reference well. Okay, then I enable it this. Now what I will do is I will go for the subtraction here. In the subtraction I will use a reference wells. We have a different referencings. So we call it as a parallel referencing, then the double referencings and all. So depending upon the experiments, sometimes you find a non-specific binding. That time you have to go for the double reference or the parallel reference. But this experiments actually prior to any experiments when you are going to set up, take a sensor, single sensor, dip into the analyte. Okay, no immobilization, no nothing. When the sensor, when you dip into the analyte, your analyte should not interact with the sensor. It indicates that there is no non-specific binding. What happens is generally these proteins are the Cha species. It's a fiber optic is a selenol, O minus, okay. Then you have protein is a positively charged, there is a possibility of the tendency to attack on this glass. Then maybe you can see the binding observation. So that's why we add surfactants in that. But if you are getting a non-specific binding, you have to address that non-specific binding first, and then you have to go for the experiment. So in this case, actually it is a very well tested molecule, and IgGs in presence of the tween as well as the BSA, it will not show any non-specific binding. So that's why I went directly with that experiment. So what I enabled the reference well subtraction. Then the align y-axis. What do you mean by alignment here? I will enable this. Align to baseline. What exactly the baseline is here? What exactly it do is, so end of your baseline, I need a very stable baseline. End of your baseline, last 10 seconds it will take it, and the beginning of your association, origin 0. So data get aligned. I will take it align y-axis to the baseline. I had done a 60 seconds. I will take a last 10 seconds of your baseline. So 50 to 60. I will put a 50 to 60. Then there is an interstep correction. One more function is there. What exactly interstep correction is? Nothing but when you are performing the baseline and the dissociation in the same well, we can use this function, interstep correction. So what it does? End of your association, beginning of the dissociation, that data get aligned because it works on the dip and read. Sensor move from one well to other well. When it dips, there may be possibilities of you can observe some jumps. So those jumps has to be aligned. So that's why we use this interstep corrections. And then Savetzke-Golay filtering, that is for the smoothing function. The sensogram gets smoothened. So then we say the process the data. When you process, this is your raw data, this is the subtracted data, and then when you look at the alignment y, as I mentioned, end of your baseline, beginning of the association, then the align axis data is nothing but end of your association, beginning of the dissociation get aligned. So this is the perfect sensogram. So we had done the processing of the sensogram. Now we have to do the analysis. The next window is your analysis here. In the analysis, we have fitting models. We have different fitting models. 1:1 fitting model, 2:1 fitting model, 1:2 heterogeneous. There are different binding models are there. So generally, when you do any biomolecular interactions, we try to fit for 1:1. One protein binding to the corresponding one. There may be some situation in the biological process. There may be a 2:1 heterogeneous binding model, or 1:2 bivalent models, and all that. So we have to choose the right one. If you know thoroughly, because when you are doing a publication, say suppose I got a 1:1 fitting data that was not giving a good fit, but you went for the 2:1 fitting model. Then you submitted a manuscript to some journal. Then the reviewer will ask you one question. You have mentioned the fitting 2:1 binding model. Do you have any supporting data by any other technique? It is a 2:1 interaction. You have to provide. Generally, reviewer asks this question for any papers. So that's why we always try to fit for a 1:1 interaction. Otherwise, if you have a ITC data with a 2:1 stoichiometry, then that's good enough. Or otherwise, you have to establish that. Or otherwise, you have to modify your protocol where you get a 1:1 interaction. So then we have a fitting models. I had chosen a 1:1 binding model, and then fitting in the fitting, what is local fitting and the global fitting. Local fitting is nothing but the calculating the K on, K off as well as the KD values corresponds to each binding curves, sensograms, each concentration. It fit each one. When you go for the global fitting, it will consider the mean of your calculation, all the binding curves. Generally, when you are publishing a data, people prefer for the global fitting data rather than the local fitting. So we will go with a global fitting. So what we do is global fitting is I will choose here, because each sensogram also giving a 1:1 color, but I want to make it into a 1 color in a 1 group. So what I will do is I will select here, right click it, set color by. I will choose one blue color here, this, and then I will say go. If you look at all the sensograms become blue color, it become a one group kind of thing. So what I will do is global fit, group by color I am using, and Rmax unlinked by sensor. I am choosing the Rmax unlinked by. There is a experimental design Rmax linked and Rmax unlinked. Rmax linked when we are doing is, suppose I am taking a one sensor, I am passing all the concentration on to the particular sensor. Then we call it as a Rmax linked. Because I had taken a 6 concentration, all the 6 concentration if I passed on a one sensor, that is Rmax linked. But my experiment here in the high throughput, what I am doing is 6 sensor or 7 sensors I had taken, and each concentration I probed with the 1:1 sensor. That's why I am unlinking that. So I am using Rmax unlinked. So this is then say fit curve. Okay. When you do the fit curve, if you look at this is the association. The red one is your theoretical, and the blue one is your experimental. So if you go here this, then you can get the, in the tabular column you have a KD. It is KD is around 3.7 nanomolar, and your K on 4.28 into 10 to the power of 5, and the K dissociation 1.5 into 10 to the power of -3. So we can say how my fit is good. We have statistical parameter also in that. My fit is good or not. My acceptance is something like that. If my R square, the regression coefficient for the fitting, if I am getting a more than 0.95, then it is a good fitting. I am getting around 0.99, it is a good fit. And how significant is my fit is? It is the goodness of the fit and significant of the fit. There are 2 parameters. We have one more statistical parameter called as a chi-square. My chi-square should be less than 3. I am getting around 0.12. So the fit is good. So when your R square is more than 0.95, automatically your chi-square also comes down. If it is fitting is not good, then you can see your difference in the chi-square as well as the R square. So this is about the data. Or you wanted to look at how my each concentration, if you want to exclude something concentration, because I have run 6 concentration, 4 or 5 concentration is good enough for the publication. So if I look at this data, if you look at this is not good, so I can exclude this. Just if I uncheck, this is okay. The next, so one concentration I am excluding, still I can do the fitting. KD is not changed much, but R square somewhat changed. So then what I will do is I will save report. When I save report, export, you have an Excel sheet report, You have experimental summary here, sensor tray where you had placed your sensor, then processing parameters, how you had done the processing of the data, sensor data where you had kept the sensor, sample data, how you had, where you had placed the samples and all that in the plate. This is your raw data. Then the processing data, this is raw data, subtracted data, align Y, align X, all these data parameters. Then the stacked graph, this is the fitting model, and this is the residual view. Residual view is nothing but the difference between your experimental and the theoretical, how the residual fit is, that is one. And the results table, where the table you have a KD calculations, errors, K on, K off, statistical parameters, all informations you can find here in this. Okay. Then you have a iso affinity graph. Iso affinity graphs play a very important role when you are performing a screening kind of experiments, where it will plot a K dissociation versus K on. So say suppose giving an example, you have a 10 batches of some proteins, your all 10 batches are behaving similar, then all data points will be come into the same cluster, then you can say that it's on par, everything is passing. If it is some of the batches are something falling that side and this side, it is deviating from that. It is very important when you do industry kind of a platform, or when you are doing a validation or such kind of experiments. Steady state analysis is there, one more, but this experiments, it is not reaching steady states. I will tell you, because protein A have a probability of binding a 4 IgGs. One protein A can take up a 4 IgG. That's why it never reaches the equilibrium. Or otherwise I have to load very less, just a 0.1 nanometer or a 2 nanometer, then I can observe the steady state. So that also, steady state is a very important, where steady state when happens is your A plus B is equal to AB complex, right? 50% A plus B is complex formation, and also this complex simultaneously dissociates back to the A and B. So this phase is called as the equilibrium. So such kind of data we go with the steady state analysis. And the group view, this if you want, if you are performing some other kind of a presentations and or I think different batches when you are running, you can get the sensograms, those things. So these are the report format, and says the good advantage is like that you want to, this fitted results you want to use for some other software. Like say suppose you want to, this data you want to review in or analyze in a BIA core software, yes, it is possible. Or you want to use a scrubber third party software, yes, you can do using this. Multiple options are there. Very easy, very quickly you can determine the kinetics on rates and the off rates. And you have fitting different models are here. 1:1, 2:1, mass transport we have, bivalent analytes we have, different models are there. So this is what about the kinetics. In quickly, hardly we had not taken a much time, around roughly less than 1 hour we finished experiment.
So this now completes the 2 lectures on Bio-Layer Interferometry for studying biomolecular interactions, where we discussed this with application scientist Mr. Sushil Vaidya from Paul Life Sciences, and he gave you some basic understanding as well as hands-on demonstration session of this novel technology platform. We will continue discussion about new technology platforms for doing biomolecular interactions in the next lecture. Also we will continue with another technology platform for biomolecular interaction analytics using microscale thermophoresis or MST technology along with Tycho NT technology. So these new technology platforms will be discussed in next lecture. Thank you.